Mars is supposed to be humanity's backup plan, but that idea falls apart the moment you look at the real planet. Mars is not just hard to live on, it can weaken people, break machines, and turn one colony into a chain of risks that reaches back to Earth. And that means the real danger is not just that Mars colonization could fail, it is that it could make humanity less secure than before. Mars is sold as a backup Earth. That is the first problem, because the label makes the planet sound much safer than it is. People hear backup and think of something hard but usable, like a second house in a rough neighborhood. Mars is nothing like that. The atmosphere is extremely thin and mostly carbon dioxide. The surface pressure is only a tiny fraction of Earth's. The gravity is just 38% of Earth gravity. The average temperature is far below freezing. If you stand on the open surface without a full life support system, you're in a lethal environment right away. That is not a difficult frontier. That is a place where basic human survival is impossible unless machines keep doing the work that Earth does for free. That matters because the language changes the way people judge the risk. If Mars is framed as a backup, then every engineering shortcut starts to sound more acceptable. Every optimistic promise sounds more reasonable. Every delay in solving a major problem starts to feel temporary. But the starting point is not temporary. The starting point is that Mars does not naturally support human life at all. And this is where people get misled. Mars looks familiar in exactly the ways that can make you careless. The length of the Martian day is close to Earth's. It has seasons. It has polar caps. It has giant volcanoes, huge canyons, weather, dust storms, sunrise and sunset. When people see those things, they instinctively put Mars in the same mental category as Earth. They think this is a harsh planet, but still a planet you can adapt to. That is the trap. The similarities are real, but they are mostly surface-level similarities. They make Mars easier to picture, not easier to live on. The atmosphere cannot support breathing. It cannot protect liquid water well at the surface. It cannot shield you the way Earth's atmosphere does. On Earth, the environment around you is doing a massive amount of invisible work every second. It gives you pressure, breathable air, stable water, temperature moderation, and protection. On Mars, almost none of that help is there, so this visual familiarity can push people toward the wrong conclusion. Mars feels close enough to Earth to create confidence, while the actual conditions remain extremely hostile. Then there is an even bigger problem above the surface. Mars does not just lack comfort, it lacks one of the planet-scale protections that helped Earth stay habitable over long time scales. Mars has no present-day global magnetic field like Earth does. It only has scattered crustal remnants from an ancient magnetic system that shut down a very long time ago. That matters because Earth's magnetic shield helps protect the planet from the solar wind. Mars lost that kind of protection more than 3.5 billion years ago. Over immense spans of time, an unprotected world can lose atmosphere far more easily. Missions like MAVEN help confirm that solar wind stripping is not just theory. It is part of the reason Mars became the world we see now. That changes the whole story. A colony would not be arriving at a healthy world that simply needs development. It would be arriving at a world that already lost the larger planetary conditions that once made it more habitable. Mars is not waiting to become Earth-like. Mars is the result of a planet moving away from that state. And that leads to the next hard point. Mars is not only dangerous now, Mars is also evidence that habitable conditions can collapse. The geological record strongly suggests that ancient Mars had liquid water and much more moderate conditions than today. It may once have had lakes, rivers, and a very different climate. Today it is cold, dry, thin-aired, and exposed to much more radiation. That transformation should be treated as a warning, not just as interesting background science. Mars is showing you in plain sight what a failed habitable world looks like. So if you are talking about building a civilization there, you are not starting from a blank slate. You are trying to build on top of a planet whose own history says that long-term habitability already broke down. You're not working with the environment. You're working against it at every level. The pressure is wrong, the air is wrong, the temperature is wrong, the radiation environment is wrong. The planet is not neutral. It is actively missing the conditions that make open human life possible. That is why the real question is not just, can humans survive on Mars? That question is too small. Humans can survive in lots of extreme places for a while if enough technology is wrapped around them. The bigger question is whether Mars can ever become a true second home for civilization, or whether it only creates the appearance of one. Because once Mars gets presented as Plan B, the stakes change completely. Then it is no longer just about a mission. It is about how humanity allocates trust, money, talent, and attention. If Mars is actually a dependency trap rather than a real second cradle, then overcommitting to it could make humanity less secure, not more secure. You could end up weakening resilience on Earth while building a settlement that never becomes truly independent from Earth in the first place. That is the opening danger in this entire story. Mars sounds like insurance. Mars sounds like survival. Mars sounds like the place humanity goes if Earth fails. But the actual planet does not support that confidence. The actual planet says something much harsher. It says that every breath, every drop of water, every safe room, every farm, every hospital, and every child would exist only inside systems that have to work all the time, with almost no room for error. And once you accept that, the next part gets even worse. Because the colony story does not begin when people land. It begins months earlier, in deep space, while the journey is already wearing them down before Mars even arrives. The trip to Mars is already a health crisis before anyone even lands. A lot of people talk about going to Mars like it's a destination problem. They focus on the base, the habitat, the landing, the first colony, but the damage starts much earlier than that. You do not simply go to Mars and then begin dealing with Mars. First you spend months inside a spacecraft, and that part matters far more than most people realize. A realistic trip is not a few days, and it is not a quick emergency mission where you can turn around easily. The transit can take roughly 180 to 200 days each way, and public mission planning still frames the journey in the range of around 7 to 10 months. So before the first person starts building anything, before the first machine starts mining anything, before the first greenhouse even exists, the crew has already spent most of a year in deep space. They are not in low Earth orbit. They are not under the protection of Earth's magnetic shield. They are not close enough for quick rescue. They are sitting in a small artificial environment with no realistic fast abort path and no hospital waiting on the other side if something starts going wrong. That changes the entire story. The colony does not begin with healthy humans arriving on a hostile planet. It begins with humans being worn down in transit and then expected to perform immediately after landing. And the most important part is that this is not guesswork anymore. We already have direct measurements that show what deep space exposure looks like. Curiosity carried the radiation assessment detector during its trip to Mars, and it measured the cruise environment on the way there. The numbers were serious. During the cruise phase, the average dose was around 1.8 millisieverts per day. On the surface, the early measurements were lower than cruise, but still around 0.64 to 0.67 millisieverts per day. The famous estimate tied to that mission put a round-trip mission plus surface stay on the order of about 1 sievert. That is not some dramatic sci-fi warning. That is measured exposure. That is biology taking a hit every day for months. And that daily accumulation matters because human beings do not experience radiation like a movie scene. It does not have to be one giant blast to be dangerous. It can be repeated exposure that keeps adding up while the crew is trying to sleep, work, repair systems, manage stress, run navigation, handle maintenance, and prepare for entry and landing. By the time they see Mars out the window getting bigger, they may already have absorbed a very large dose compared to anything normal on Earth. Then the problem gets worse, because radiation is not just one category of risk. People often reduce it to cancer and leave it there, as if the danger is mostly something that appears decades later. That is incomplete. NASA's human research work treats radiation as a cancer risk, but it also flags possible effects on the central nervous system and on human performance. That means the issue is not only whether the crew gets sick later in life, the issue is whether exposure can affect the people who are supposed to keep the mission functioning while the mission is happening. Judgment matters on a Mars transfer. Attention matters, memory matters, emotional control matters, fine motor performance matters, problem-solving matters. If the same environment that is already punishing the body can also push on cognition and performance, then the people who are responsible for survival may be doing that job while their own sharpness is under pressure. That is the part many Mars discussions skip over. The crew is not just being transported. The crew is the operating system of the mission. They are the mechanics, the medical staff, the emergency response team, the decision makers, and the backup for every failure mode. If their bodies are under constant stress and their minds are under constant strain, then the whole mission starts carrying hidden instability long before the colony phase even begins. And even that still understates the danger, because deep space radiation is not constant in a simple way. It can change, it can spike, it can hit harder at the wrong time. Solar activity makes the trip non-linear. Curiosity's cruise data showed that solar energetic particles made measurable contributions to the total cruise dose, and Mars missions have also shown that radiation conditions can jump with solar activity, so the crew is not moving through a calm, empty corridor between Earth and Mars. They are moving through a variable radiation environment. Most days may be bad in an ordinary way, and then one badly timed solar event can suddenly turn the trip into something much more dangerous. That matters because a spike does not arrive by itself. It arrives on top of everything else the crew is already carrying. Months of confinement, months of disrupted sleep, months of maintenance work in a tight volume, months of limited privacy, months of knowing that no one can come get you, months of watching every piece of equipment because a small malfunction can become a big mission problem. Add a radiation event to that and the crew is not just getting extra exposure. They are dealing with a layered crisis inside a system that already has little room for mistakes. And there is another hard truth in this. Deep space does not care when the crew is busiest. A serious event could happen during a maintenance problem, during a medical issue, during a conflict between crew members, during a navigation phase, or during a systems anomaly. So the risk is not simply the size of the dose, the risk is the timing. A dangerous exposure at the wrong moment can hit exactly when the crew most needs stable judgment and full performance. That is why the trip itself has to be treated as the first stage of colony failure risk. If you start with the idea that the settlers arrive ready to build, you're already making the wrong assumption. By the time colonists land, they may already be degraded in several ways at once. They may have taken months of radiation exposure. They may be physically deconditioned from the travel environment. They may be carrying the mental strain of isolation, confinement, and long-duration mission stress. They may be exhausted from the simple fact that living inside a spacecraft for that long is a constant operational burden. And then the second they arrive, they are expected to do some of the hardest work of the entire project. The early population on Mars will not have the luxury of specialization in the way a mature society does. The first settlers will be everything. They will be the emergency response system. They will be the repair crew. They will be the medics. They will be the labor force. They will be the backup for one another when something breaks. So if that founding group starts compromised, the colony is not beginning at full capacity. It is beginning in deficit. That is a very serious point because first settlements are the most fragile stage of any colonization effort. There is less redundancy, less infrastructure, less margin, and less room for slow recovery. If you land with a crew that is already not operating at 100%, then every later problem becomes harder to contain. Repairs take longer, mistakes are more likely, conflicts become more dangerous. Medical issues become harder to manage. Small failures can combine faster. So when people picture Mars colonization, they often picture a dramatic landing followed by the start of a new chapter. But that skips the reality. The new chapter does not open with a fresh team. It opens with a team that may already be carrying months of accumulated damage before the real planetary risks even begin. And that leads to the next problem. Because once they arrive, the radiation issue does not end. It changes form, but it stays with them, and now it starts threatening not just their survival, but their competence. Radiation on Mars is not just a health problem, it is a competence problem, and that makes it much more dangerous. On Earth, When people talk about radiation, they usually think about medicine. They think about long-term cancer risk, exposure limits, and individual health outcomes. On Mars, that frame is too narrow. In a colony, radiation does not stay inside the category of personal health. It spreads into the performance of the whole system. NASA's own risk work does not stop at cancer. It also points to possible cardiovascular effects and possible effects on the central nervous system. That means the issue is not only whether someone gets sick later. The issue is whether the people doing the most important jobs in the colony stay reliable enough to keep everyone else alive. That changes everything. A Mars settlement is not held together by comfort. It is held together by people doing precise work under pressure. Pilots have to land cargo safely. EVA crews have to work outside without making mistakes. Doctors have to diagnose and treat problems with limited resources. Reactor operators, power technicians, habitat engineers, communication staff, and mission leaders all have to make good decisions again and again with almost no margin for error. On Earth, a society can absorb some decline in performance because there is redundancy everywhere. Other people can step in. Systems can fail without killing everyone nearby. On Mars, that is much less true. If the environment is steadily pushing critical operators away from peak function, then radiation stops being a medical issue and becomes a systems issue. The colony is not just trying to protect bodies, it is trying to protect judgment, speed, accuracy, attention, and discipline. And landing on Mars does not solve that, it only changes the exposure pattern. A lot of people hear that the Mars surface is better than deep space, and assume that means the problem is mostly over once the crew arrives. That is not the right way to think about it. The surface is safer only in a relative sense. Mars does have an atmosphere, and that atmosphere does reduce exposure compared with open cruise space. But Curiosity's surface readings still imply natural radiation levels far above normal Earth background. So there is no clean moment where the colony moves from danger into safety. The settlers are still living inside a chronic exposure field. The dose keeps building. The clock keeps running. That matters because colonies are not static. They do not just sit quietly inside perfect shelters. People have to leave habitats. They have to do surface work. They have to build, repair, inspect, transport, and expand. Every EVA adds exposure. Every delay in burying habitats adds exposure. Every long outdoor construction job adds exposure. Every habitat breach that forces extra repair time adds exposure. Every period where shielding is incomplete or compromised adds exposure. Mars is not giving the colony a safe zone with occasional hazards around the edges. It is giving the colony a constant hazard that has to be actively managed every day. And once you understand that, one conclusion becomes unavoidable. Shielding is not just one engineering detail among many. Shielding becomes the thing that defines what the colony really is. If survival depends on thick shielding, underground spaces, regolith piled over habitats, storm shelters, shielded medical rooms, protected work tunnels, and tightly controlled EVA schedules, then the real measure of a Mars settlement is not headcount. It is protected volume. That is what determines how many people can live there, how long they can stay there, how many can be treated during a crisis, and how much work can be done without pushing exposure too high. On Mars, habitable space is not simply whatever you can build. It is whatever you can protect well enough for humans to function inside it. That has social consequences immediately. Who gets access to the best shielded rooms? Who gets moved into safer areas during a solar event? Which functions get the most protected corridors, and which crews have to spend more time outside? Who gets shielded medical space if there is not enough for everyone? Those are not abstract questions that appear much later in the life of the colony. They are built into the physical design from the start. The layout of the settlement becomes a survival hierarchy. Control the protected spaces, and you control the colony's real centre of power. And radiation still does not stay in its own lane even then, because it interacts with other weaknesses instead of remaining a separate problem. This is where Mars becomes much harder to think about in a simple way, People like lists, radiation, low gravity, sleep problems, stress, microbes, limited food, isolation. That sounds manageable because a list makes problems feel separate. But NASA's immune risk research points in the other direction. Radiation interacts with other stressors such as microgravity and poor sleep in ways that can alter immune response. That means the risk picture is not additive, it is interactive. One weakness can make another weakness worse. So a colonist is not just dealing with radiation. That same person may also be sleeping badly, working in confinement, carrying chronic stress, adapting to lower gravity, breathing recycled air, and living inside a controlled microbial environment that does not behave like Earth. Nutrition may also be limited or imbalanced during certain phases of the mission. Now the problem is no longer one threat at a time, it is overlap. Radiation arrives attached to all the other pressures of Mars life. That matters because overlap is where reliability starts breaking down. A person whose sleep is bad may recover more slowly. A person under constant stress may think less clearly. A person with altered immune response may get sick more easily or recover more slowly from illness. A person already physically strained by the long work cycles may make worse decisions when exposed to higher stress or higher carbon dioxide levels. So when you ask whether Mars risks are survivable, the real question is not whether each risk can be tolerated alone. The real question is, what happens when the same small group of people has to absorb all of them at once, while still keeping a fragile settlement functioning perfectly? That is why Mars stops looking like a set of engineering problems with independent solutions. It starts looking like a tightly linked system where each weakness can amplify the others. Radiation is part of that network. It does not just threaten health in a narrow sense. It helps push the colony toward a state where performance, resilience, and recovery all become harder to maintain at the same time, and that is where the extinction angle starts to appear in a more serious form. A Mars program is often sold as species insurance. The argument sounds simple. If Earth is vulnerable, build another branch of civilization somewhere else. But if the off-world branch depends on a small number of people staying highly competent while the environment steadily pushes them away from full competence, then the insurance logic starts to reverse. You are not building a robust backup. You may be building a frontier where chronic operator impairment becomes normal. That is a very dangerous foundation for any society, especially one that depends on perfect execution. On Earth, a bad engineering call can be expensive, embarrassing, or tragic in a limited way. On Mars, a bad engineering call can kill everyone in a habitat. A delayed maintenance choice can become a fatal air problem. A weak shielding plan can become a long-term medical crisis. A badly timed EVA decision can cost a crew that the colony cannot replace. When the environment is this unforgiving, even a small decline in performance has consequences that scale up fast. So the real danger is not that radiation simply kills people one by one. The deeper danger is that it can slowly lower the quality of the decisions made by the exact people whose decisions matter most. That is much harder to see, much harder to dramatize, and in some ways much worse. A colony can survive illness more easily than it can survive declining competence in its most critical operators. If your pilots, engineers, medics, and commanders all need to stay sharp to keep the system alive, and the environment keeps working against sharpness, then the colony is balanced on extremely thin margins from the beginning. And the next part of the problem goes even deeper, because radiation is only one way Mars works against the human body. Even if you built better shields tomorrow, you still have the planet's gravity pulling in the wrong direction for human biology. Radiation is bad enough, but low gravity creates a different kind of danger, because it works slowly and it can make damage feel normal while it is happening. Mars gravity sounds like a reasonable compromise at first. It is not zero-G. You're not floating all the time. You can walk, lift things, work on the ground, and move through built spaces in a way that sounds much closer to ordinary life. And that is why a lot of people hear 38% of Earth gravity and assume the body will mostly adapt. That assumption is doing a lot of work, because right now we do not actually know that 0.38 grams is enough to preserve long-term human health. And that uncertainty matters because the data we do have from long-duration spaceflight is already serious. In space, weight-bearing bones can lose around 1% to 1.5% of density per month even with countermeasures. That is not a small effect. That is the body reacting to reduced loading by quietly dismantling itself. Mars will probably be less severe than orbit, but less severe is not the same thing as safe. Less severe is not the same thing as stable over years. And it is definitely not the same thing as proving the human body can live under those conditions across whole generations. That is the first problem with the Mars gravity argument. People treat it like an answer when it is really a partial unknown. It may be enough for some functions, it may be enough for some adults for some period of time, but colonization is not about surviving for a while. Colonization means building a place where bodies still work after years, after decades, and eventually across childhood, adulthood, pregnancy, aging, and death. There is a huge gap between better than 0G and good enough for civilization. And the body does not only respond through bone. Reduced gravity reaches into muscle, heart function, stamina, recovery, and physical performance in general. NASA's own human risk work treats reduced cardiorespiratory and musculoskeletal fitness as major hazards in long-duration missions. That sounds clinical, but in a Mars colony it becomes very practical very quickly. The people there are not training for abstract health markers. They have to do hard work in a dangerous place. They may need to haul equipment, lift components, carry emergency supplies, crawl through maintenance spaces, rescue injured crew, move someone in a suit, force open a difficult mechanism, or keep working after partial system failures. That is physical labour with high stakes. So if the colony's population is gradually getting weaker in the same environment that demands strength and endurance, then low gravity is not a background medical issue. It becomes an infrastructure issue. The settlement depends on bodies that can perform under stress. If those bodies lose capacity over time, then every task becomes harder. Repairs take longer, emergencies get more dangerous, rescue becomes less reliable. Even normal daily work starts consuming more of the colony's limited energy and time, and Mars makes that worse because the environment already adds resistance everywhere else. Suits are heavy and awkward, even if Mars gravity makes them feel lighter. Airlocks slow movement, pressure systems create bottlenecks. Outside work is exhausting. Every emergency response will happen inside a place with narrow margins, limited medical support, and little room for physical weakness. On Earth, if one worker is tired or injured, a large support structure can take over. On Mars, a small decline in group fitness can affect the entire colony's operating ability. Then there is another issue that sounds less dramatic until you think through the consequences. Vision may also change. One of NASA's major concerns from long-duration spaceflight is spaceflight-associated neuroocular syndrome, often shortened to SANS. It has been linked to headward fluid shifts and structural changes involving the eye and visual system. In simple language, living in space for long periods can change vision in ways that matter. Mars gravity might change that compared with 0G, but that is not the same as proving the risk goes away. Right now, there is no large human dataset showing that 0.38G fully protects against it. That matters a lot more than people think. A Mars colony depends on precision. It depends on people reading instruments correctly, doing technical work with their hands, spotting defects, navigating during EVA, piloting vehicles, performing surgery or medical procedures, managing robotics, reading screens, inspecting seals, and making accurate spatial judgments under stress. If long-duration reduced gravity changes vision even in a minority of settlers, that can directly affect safety and competence. And notice the pattern again. This is not one isolated health problem. It is another way the environment can push critical operators away from full performance. Mars is not only asking humans to survive, it is asking them to stay physically capable and technically precise for very long periods in a setting where failure can cascade fast. Then the question gets even more serious, because adults are only the beginning of the story. A real colony is not just a workplace. It eventually becomes a place where people are born, grow up, and age. That is where the evidence becomes very thin. This is the hidden frontier in all Mars colonization talk. Childhood under 0.38 G are giant unresolved questions. If adults already show major changes in bone, muscle, vision, immune behavior, and general physiology in reduced gravity or space environments, then pregnancy on Mars is not a minor extension of what we already know. Childhood development on Mars is not a solved problem waiting for scale. Puberty, skeletal development, brain development, cardiovascular development, and aging under partial gravity are still enormous unknowns. That means a Mars outpost and a Mars colony are not the same thing at all. An outpost might function as a rotating industrial or scientific camp, where adults go for defined periods and then return. That is hard but conceptually simpler. A real colony means you are claiming that human biology can continue there across generations. Right now, the evidence for that is almost non-existent. And this matters because the public story often skips straight to families, schools, neighborhoods, and a permanent branch of civilization. That leap is much larger than it sounds. Before you can honestly describe Mars as a second home, you would need answers to questions that go far beyond whether a trained adult can survive there for a few years with strong support. You would need to know whether children can develop normally. You would need to know whether pregnancy is safe enough. You would need to know whether aging under 0.38 grams creates new long-term damage. You would need to know whether a Mars-born human body can thrive there without becoming trapped by the very planet it was born on. And that leads to the hardest point in this entire section. Gravity itself could make Mars permanently dependent on extreme technology. If settlers need constant exercise just to slow decline, that is dependency. If they need highly tailored medicine to offset the effects of low gravity, that is dependency. If they need artificial loading systems, rotating centrifuge habitats, or some form of higher G rehabilitation to remain functional, that is dependency. If Mars-born people cannot safely visit Earth, or Earth-born people cannot stay healthy on Mars without continuous intervention, then this is not a self-sustaining civilization in the ordinary sense. It is a long-term managed condition. That changes the meaning of colonization completely. A self-sustaining society should be able to reproduce its basic conditions of life without remaining permanently trapped inside a medical support framework. But if the human body never truly adapts to 0.38 G across generations, then Mars does not become a second cradle. It becomes a place where people can only persist through constant technological correction. That is not independence. That is life under permanent compensation. So low gravity is not just a challenge to comfort. It may be a challenge to the basic idea that Mars can ever support a normal human civilization. And if the body itself is under that kind of pressure all the time, then the next threat becomes even more dangerous, because it attacks both people and machines at once. Dust sounds like a maintenance problem. On Mars, it can become a survival problem. A lot of people picture Martian dust as annoying but manageable, like desert dust on Earth getting into equipment and needing regular cleaning. That is far too mild. Mars missions keep running into the same basic fact again and again. Dust gets everywhere, and once it gets in, it starts causing trouble across multiple systems at the same time. NASA and JPL have been warning about this for years. Dust and regolith can foul mechanisms, jam instruments, wear down moving parts, and reduce hardware performance. Perseverance is studying regolith partly because engineers already know this material matters for future human missions. And one of the clearest warnings came years earlier, with Opportunity. That rover survived far longer than expected, but a planet-encircling dust storm reduced sunlight so much that its solar power collapsed, and it never came back. That was a robot. A human settlement would have many more systems, many more points of failure, and far less tolerance for interruption. So dust on Mars is not background scenery. It is part of the operating environment that is actively working against machines all the time. And the dangerous part is that this problem scales with activity. The more serious your colony becomes, the more surface work it has to do. That means more rovers moving, more excavation, more construction, more cargo unloading, more EVA traffic, more mining, more regolith handling, more air lock cycles. In other words, the more you try to build a civilization there, the more you expose that civilization to a material that is already known to be hostile to hardware. Then the problem gets worse, because the danger is not just mechanical, the chemistry is bad too. Martian soil is not just dusty, it contains compounds that complicate human survival and industrial use at the same time. Phoenix found perchlorates in Martian soil. Curiosity later found more chlorine-oxygen signatures consistent with perchlorate-like compounds. NASA has described Martian perchlorates and chlorates as hazardous to human health even at low concentrations. These are oxidizers. That means they are not just something you would prefer to avoid. They can interfere with biology, corrode equipment, and complicate water use and processing. That changes the whole picture for colonization, because regolith is supposed to be one of your biggest local resources. People talk about using local soil for construction, for extracting useful materials, for shielding, for making bricks, for growing plants after treatment, for various forms of in situ resource use. But if the same material you want to build with is chemically hazardous, then every use case becomes more complicated. Every excavation step can become an exposure step. Every water extraction step can become a contamination control problem. Every construction process may need extra cleaning, filtering, chemical treatment, or isolation procedures. So the soil is not just hard to work with, it is actively forcing more engineering burden onto a colony that already has almost no spare margin. And then there is the part that makes the health risk much more serious than people usually assume. It is not only what is in the dust, it is the size of the particles and where they can go. Fine Martian dust is dangerous partly because it can reach places that are hard to protect. Recent toxicology work using Martian dust analogues points to risks such as cytotoxicity, oxidative stress, and inflammatory responses. Reviews of dust hazards also flag silica, gypsum, nanophase iron oxides, perchlorates, and trace metals as concerns. You do not need every part of that science to understand the practical problem. Very small adhesive particles are hard to keep out, hard to remove fully, and dangerous because they can spread into both people and machines. If that dust gets into lungs, it becomes a medical issue. If it gets into eyes, it becomes a medical and operational issue. If it gets into suit joints, seals, bearings, filters, pumps, valves, or electronics, it becomes a maintenance issue. If it gets into a food system, crops, water lines, or air handling, it becomes a colony-wide contamination issue. This is why Martian dust is not one hazard on a list. It is a universal contaminant. It can connect medicine, maintenance, agriculture, environmental control, and crew performance into one shared failure chain. That is the real problem. On Earth, you can often isolate categories of failure. A dirty machine is one issue, a respiratory problem is another, a crop issue is another. On Mars, the same fine material can participate in all of them at once, and because the colony is closed and resource limited, you do not get to solve each problem independently. A filter clogged by dust affects air quality. Bad air affects crew performance. Reduced crew performance affects repairs. Delayed repairs increase system stress. System stress increases risk elsewhere. That is how a contamination problem turns into a systems problem. And there may be another layer to this that makes it even harder. Mars dust may not just be chemically and mechanically aggressive. It may also be electrostatically difficult. NASA-backed work on electrostatic dust removal exists for a reason. Dust sticking is not a minor inconvenience. It is a real operational issue. Recent observations on Mars have also documented atmospheric electrical discharges associated with dust activity. That means the threat may not stop at particles being abrasive or toxic. It may also involve electrical behavior that affects how dust clings to surfaces, interacts with materials, interferes with instruments, and possibly even influences local atmospheric chemistry. That matters because static charged dust is even harder to manage in practice. If the particles cling to suits, panels, optics, seals, radiators, and mechanical interfaces, then just brushing them off is not enough. Now you need dedicated removal systems, anti-adhesion strategies, more robust cleaning procedures, and extra design protection across equipment that is already under pressure from cold, radiation, and wear. On a planet where the outside environment is constantly trying to push itself into every joint, every lock, every air seal, and every moving mechanism, electrostatically active toxic dust becomes one more reason why routine work is never routine. And once you zoom out to the colony level, the consequence is harsh. You do not get to isolate the dust problem to one department. If dust is getting into airlocks, then habitat operations are a dust problem. If it is getting into lungs and eyes, then medicine is a dust problem. If it is degrading filters and seals, then life support is a dust problem. If it is coating solar arrays and optics, then power is a dust problem. If it is contaminating water handling and crop systems, then agriculture is a dust problem. If it is wearing down rovers, drills, conveyors, and excavation gear, then logistics and construction are dust problems. Every major subsystem of the colony starts inheriting the same enemy. And the more the settlement grows, the worse this gets. Expansion means more outside work. More outside work means more dust transport into the colony's controlled spaces. More infrastructure means more surfaces, more seals, more mechanical interfaces, more filters, more vulnerable components, and more maintenance burden. So growth does not automatically make Mars safer. In one important way, growth can make Mars more dangerous, because the colony keeps increasing its contact area with a planet that contaminates almost everything it touches. That is why Martian dust has to be treated as a core civilizational threat, not a side issue for engineers to clean up later. A settlement can maybe survive one contaminated tool, one dirty suit, one fouled filter, one damaged panel. But if dust is woven into the daily operation of every system that keeps people alive, then the colony is permanently fighting a material that is small enough to spread everywhere and dangerous enough to matter almost everywhere. And that leads directly to the next question. If the outside environment can invade every machine and every breath that easily, then what exactly is a Mars habitat? Is it a home, or is it just a life support system that has to win every hour forever? A Mars habitat sounds like a place. In reality, it is a process that has to keep working every second or people die. That is the first thing most people do not fully take in. On Mars, indoors is the real planet. The walls are not just keeping bad weather out, they're creating the only environment in which a human body can function. Air pressure has to be maintained. Oxygen has to be produced or stored and then controlled. Carbon dioxide has to be removed. Humidity has to stay within range. Temperature has to stay within range. Water has to be recovered, cleaned and reused. Waste has to be processed. Air has to keep moving. Filters have to keep working. Sensors have to stay accurate. None of that is passive, and none of that can just be left alone for long. On Earth, your house is sitting inside a living planet that already gives you pressure, breathable air, temperature moderation, water cycles, and an open environment that absorbs small mistakes. On Mars, the habitat has to manufacture those conditions itself. It is not shelter in the normal sense. It is a machine that continuously imitates a tiny part of Earth, and it has to keep doing that without pause. That already makes the whole idea of settling Mars much more extreme than people usually admit. Because once your living space becomes an active life support system, then maintenance is no longer support work around civilization. Maintenance is civilization. And the hard part is that even our best closed systems on Earth and in orbit show how difficult that really is. The ISS Environmental Control and Life Support System has only recently demonstrated the kind of water recovery level around 98% that matters for very long missions. That is a real engineering achievement. But it is also a warning. If it takes that much work, technology, testing and support to close the loop that tightly in low Earth orbit, with decades of experience and continuing contact with Earth, then a Mars habitat is not entering a solved problem. It is entering one of the hardest engineering problems humans have ever tried to live inside. And there is a second problem that makes this even more dangerous. Closed systems do not always fail in obvious ways. They can fail in strange ways slowly, and sometimes before people fully understand what is happening. Biosphere 2 is one of the clearest warnings about that. During its closure, oxygen dropped from normal Earth levels of about 21% down to around 14% over about 16 months. That was enough to create real health problems. Carbon dioxide also swung in unstable ways. And remember the setting, that happened on Earth. It happened with Earth gravity. It happened with abundant sunlight. It happened in a place where emergency intervention was possible. Even there, with far better conditions than Mars, the system proved much harder to stabilize than the optimistic vision suggested. That matters because Mars settlement rhetoric often jumps too quickly to self-sufficiency. It makes closed living sound like a scale problem, as if the main challenge is just building bigger greenhouses, better recyclers, and stronger habitats. But the history of closed ecological systems says something harsher. Stability is fragile, small imbalances can compound, hidden chemical sinks can appear, biological processes can behave differently than expected. Systems that look stable on paper can drift in real life. Mars would take all of those known difficulties and then add more stress, more isolation, more dust, more radiation, colder conditions, and much longer supply delays. And that means you do not need a dramatic hull breach to have a life support crisis. Tiny drifts can be enough. Carbon dioxide is a perfect example. People tend to think of CO2 as a threat only if it gets extremely high, but that is too simplistic. NASA's guidance is very clear that hypercapnia can cause headache, fatigue, breathing difficulty, and in severe cases, death. Separate research has also found that even concentrations below some values seen on the ISS can impair complex decision-making. That is a terrifying kind of failure because it creates a feedback loop. The colony does not need a movie-style decompression event to enter danger. It just needs air quality to drift enough that the crew becomes slightly less sharp while trying to solve the problem causing the drift. That is exactly the kind of crisis Mars makes likely. Not one giant catastrophe at first, but a small system slide that changes how well people think, sleep, work, and respond. A sensor reads slightly off. A scrubber is not performing at full capacity. Maintenance is delayed because another issue takes priority. Crew fatigue makes people slower to notice the pattern. CO2 rises enough to cause more fatigue and weaker judgment. Now the people who need to diagnose and fix the air problem are doing that work while the air itself is making them worse at doing it. That is why Mars life support is not just about surviving major accidents. It is about staying ahead of the subtle ones. And water and oxygen recycling do not remove that danger. They just move it into a more complex maintenance burden. The ISS can recover a very high fraction of water, and its oxygen systems are serious engineering achievements. But those systems are not magical. They are hardware. They require power. They require upkeep. They require monitoring. They require parts, cleaning, repair, calibration, and operational discipline. And they have been developed inside a huge support structure backed by decades of testing and resupply from Earth. Mars strips away a lot of that safety net. On Mars, those same categories of system would have to deal with dust contamination, colder environments, longer logistics chains, much more limited spare parts, delayed expert support, and no fast rescue option when a repair goes wrong. So when people say a colony will recycle its water and make its oxygen, that can sound comforting. But those words can hide the real meaning. The colony's air and water would not come from nature. They would come from machines, filters, tanks, pipes, membranes, catalysts, software, inspections, maintenance schedules, and a crew that has to keep all of it functioning under constant pressure. In other words, the settlement would not be living off the land in the way frontier stories usually imply. It would be living off a maintenance backlog. And if that backlog grows faster than the colony can control it, the result is not inconvenience. The result is direct danger to breathing, drinking, hygiene, medicine, food production, and temperature control all at once. That is why everyday life on Mars becomes existential labour. On Earth, civilization hides life support so well that most people do not think about it at all. Water comes out of the tap. Air is just there. Waste leaves the house and disappears into infrastructure. Temperature is adjustable. If something breaks, the wider environment is still not trying to kill you while you wait for repair. Mars removes that comfort completely. On Mars, life support would sit in your mind all the time because it would be the thing standing between normal life and immediate danger. Every leak matters. Every valve matters. Every sensor matters. Every unusual pump vibration matters. Every software fault matters. Every algae bloom in a recycling loop matters. Every microbial contamination issue matters. Every scrubber problem matters. Every delay in replacing a worn component matters. The colony never gets to say, "This is just maintenance, we will handle it tomorrow." On Mars, tomorrow may be exactly when the problem becomes life-threatening. So a habitat there is not a home in the normal sense. It is a defended environment. It is a tiny biosphere that has to be actively held in a survivable state hour after hour. And the more people you add, the more systems you add, the more pipes, valves, rooms, seals, filters, crops, waste streams and control software you add, the more possible interactions you create between failures that were never meant to happen together. That is the deeper point. A Mars colony would not just need to build life support. It would need to live inside life support without ever getting casual about it. The entire culture would have to revolve around keeping the artificial environment stable. That means daily life is not built on comfort first. It is built on vigilance first. And once you understand that, the next danger becomes obvious. If the habitat is a machine that has to keep manufacturing life, then power is the thing that holds the whole illusion together. And if power falters on Mars, the colony does not lose convenience. It starts losing civilization itself. Power is not just another resource on Mars. Power is the resource that decides whether every other resource still exists. That is the first thing a lot of Mars discussions hide behind technical language. People talk about energy like it is one-line item in a long engineering plan, next to food, water, transport, habitats, mining and communications. On Mars, that is the wrong way to think about it. Energy is inside all of those things. You need power to make oxygen. You need power to recycle water. You need power to control temperature. You need power to run lights for crops, pumps for fluids, fans for air circulation, computers for monitoring, heaters for survival, charging systems for vehicles, drills for excavation, tools for repairs, freezers for medicine, and communications gear to stay connected. Even survival through an ordinary Martian night depends on energy. So when power drops, the colony is not just using less electricity. It is starting to decide which parts of life it can no longer afford to maintain. That is what makes energy the master resource. It quietly contains all the others. Oxygen depends on it. Water depends on it. Heat depends on it. Mobility depends on it. Medicine depends on it. Food production depends on it. Once the energy margin starts shrinking, every other system starts lining up to compete for what is left. And that is especially dangerous on Mars because one of the most obvious power options also has a built-in enemy. Solar works there, but Mars also attacks solar constantly. This is not theoretical. Mars dust storms can sharply reduce sunlight at the surface. NASA has been clear about that for years. The most famous example is Opportunity. That rover survived an extraordinary amount of time, but a global dust storm cut its solar power so badly that it never recovered. InSight had its own struggles as dust built up on its panels and slowly reduced available energy. Those were robotic missions. They did not need breathable air. They did not need medical support. They did not need heating for a human settlement. They did not need to keep crops alive, preserve food, recycle water, and run a full habitat. If a robot can die because the sky gets dark for long enough, then a human colony that leans too hard on solar alone is taking a very serious gamble. And the danger is not only one giant storm. Dust can hurt you in slower ways too. It can accumulate on panels over time. It can reduce efficiency before anyone calls it a crisis. It can force the colony to spend time and labour cleaning systems that are already hard to access. It can create a situation where output is not dead, but weaker than planned, which means the settlement starts running with less margin than expected. That kind of power stress is dangerous because it does not look dramatic at first. It just keeps forcing more compromise, maybe fewer greenhouse lights, maybe less industrial work, maybe delayed water processing, maybe less battery reserve, maybe more maintenance deferral. And on Mars, repeated compromise is how stable systems start turning fragile. NASA's own studies show why this is not a small design issue. The scale problem is built in from the beginning. Surface power analyses for Mars missions have shown expedition-level loads in the range of tens of kilowatts, and those same studies show that dust storms can hammer solar availability in modelled scenarios. That is why NASA keeps pushing fission surface power. Reliable output that does not depend on weather, dust conditions, season, or latitude is not a luxury for Mars. It is a survival requirement. If the colony needs constant life support and constant thermal control, then it also needs a power source that does not disappear when the environment changes. But even that does not solve the real scale problem. A 40 kilowatt class fission system sounds serious, and for a small mission it is serious. But a growing settlement would eventually want much more than bare survival. It would want to run industry. It would want more shielding work, more excavation, more water extraction, more food production, more medical capacity, more redundancy, more manufacturing, more heated volume, more computing, more transport, and more reserve. That means the energy demand of a meaningful colony does not stay small. It grows with every step towards self-sufficiency, and that leads to an uncomfortable conclusion. The more serious the colony becomes, the more power-hungry it becomes. The more independent it tries to become, the more energy infrastructure it needs to support that independence. So power is not just the thing that keeps the first habitat alive, it is also the thing that can bottleneck the entire future of the colony. If energy growth lags behind population growth and infrastructure growth, then the settlement gets trapped. It can survive, but it cannot expand safely. It can maintain, but it cannot truly mature. And then there is the next hard truth. Nuclear power helps, but it does not remove fragility. It changes what fragility looks like. A reactor solves the sunlight problem in one sense. It can provide steady output through dust storms during the night and across seasonal changes. That is a huge advantage. But reactors bring their own burdens. They add mass to launch. They add engineering complexity. They raise questions about shielding, heat rejection, maintenance, spare parts, failure modes, and sensitivity. They are not magic boxes that end the energy problem. They are another class of critical system that the colony has to build around and protect. And right now, the fission surface power story is still on a development path. NASA has been moving through demonstration work with the Moon as the nearer target before Mars. So the realistic picture is not simple at all. It is not solar is flawed, so nuclear solves it. The realistic picture is that a Mars colony large enough to matter would probably need a hybrid power system. Solar for some tasks, nuclear for baseline survival loads and resilience, batteries or storage systems to buffer gaps, backup capacity for emergencies, distribution systems, maintenance capacity, spare components, controls, safety procedures, and protected infrastructure around all of it. That means more complexity, not less. More power sources can create more resilience, but they also create more interfaces, more components, and more ways for failures to interact. A dust storm can weaken solar. A maintenance issue can limit nuclear output. A storage problem can reduce reserve margin. A distribution fault can isolate part of the habitat. A thermal issue can force shutdowns. A spare parts shortage can turn a repairable problem into a prolonged power constraint. The system may be more capable overall, but it is also more tightly coupled. And that is exactly how power turns into extinction risk on Mars. A colony that loses power does not just lose comfort, it loses temperature control, it loses atmospheric processing, it loses water treatment, it loses part of its food system, it loses communications margin, it loses the ability to charge vehicles and tools, It may lose medical refrigeration, monitoring, and emergency capacity. It may lose the very repair systems needed to restore power in the first place. The moment energy collapses, every other survival system starts degrading at the same time. That is the part people should sit with. On Earth, a blackout is serious, but the atmosphere is still outside. The pressure is still outside, and the environment is still there supporting your body while repairs happen. On Mars, a blackout means the colony has less ability to defend itself against the planet around it. Heat starts slipping, air processing slows, water systems fall behind, emergency options narrow, time becomes more hostile by the minute. And the worst part is that a power crisis does not happen in isolation. It will probably arrive with something else: a dust event, a mechanical failure, a medical emergency, a communications problem, a habitat leak, a maintenance backlog. That is why power is so dangerous as a point of failure. It is the system the colony most needs when every other system is already under stress. So on Mars, losing power is not like losing a utility. It is more like losing the thing that makes the settlement a settlement at all. The moment energy falls below what survival requires, the colony stops functioning as a civilization and starts becoming a countdown. And once you understand that, the next danger becomes even harder to ignore. Because when rescue is impossible and delay is built into physics, medicine changes from healthcare into triage under isolation. The hardest part about medicine on Mars is not the list of diseases. It is the list of things you cannot do once something goes wrong. In low Earth orbit, a serious medical event is already dangerous, but there is still one huge advantage in the background. If things get bad enough, the patient can potentially be brought home. Mars removes that option. Deep space mission planning assumes communication delays that can reach about 44 minutes round trip, and it assumes there is no meaningful emergency return when someone is in real trouble. That changes medicine at the most basic level. On Earth, and even in near-Earth space, a lot of treatment decisions are made with the knowledge that a bigger hospital exists somewhere else, a specialist exists somewhere else, better imaging exists somewhere else, intensive care exists somewhere else, blood products exist somewhere else, a surgical team exists somewhere else. Mars cuts that chain. If a patient starts crashing on Mars, there is no transfer, there is no medevac, there is no real-time expert talking the crew through each step fast enough to matter in an emergency. There is only the habitat, the equipment on hand, the skills the crew already has, and the time pressure created by the patient's condition. That means Mars medicine is defined as much by absence as by capability. It is defined by the hospital you do not have, the specialist you cannot call in fast enough, the evacuation you cannot perform, the extra staff you cannot spare, and the margin you do not have. A medical problem that is serious but manageable in orbit can become lethal on Mars simply because the support system ends at the walls of the colony. And that would already be bad enough if Mars crews were otherwise healthy. They will not be. NASA already tracks a long list of human risks in long-duration spaceflight. Bone loss, fitness decline, immune alteration, eye and vision changes linked to SANS, radiation-related effects, host microbe interaction risks. That is the baseline before Mars adds its own pressures. Then you add reduced gravity, Martian dust, long EVAs, delayed communication, chronic confinement, disrupted sleep, limited fresh food, and constant operational stress. So a Mars settlement is not facing one famous signature illness. It is facing a whole medical environment that does not exist on Earth. That is the part people underrate. A Mars colony would not just bring Earth medicine to another planet. It would have to improvise a new branch of medicine in real time. And it would be doing that with a very small staff, limited gear, limited sterile space, limited diagnostics, and a patient population already under unusual biological stress. The crew would not be practicing medicine in a well-supported system. They would be inventing standards while depending on them. And once you understand that, even ordinary health problems start looking completely different. A kidney stone on Earth is painful and serious, but there is a whole chain of care behind it. Imaging, pain control, fluids, procedures if needed, monitoring, backup options. On Mars, that same kidney stone can become a major operational event. An eye injury is not just an eye injury when precision work and EVA safety depend on vision. Pneumonia is not just pneumonia when lung function, air quality, fatigue, and closed habitat infection control are already linked. Appendicitis is not just appendicitis when surgery means using precious sterile supplies, power, trained hands, oxygen, and recovery space inside a fragile life support environment. A fractured femur is not just a broken bone when moving the patient is hard. Immobilization is resource heavy, and every hour of care pulls people away from systems the whole colony depends on. Even a contaminated wound changes category on Mars. On Earth, infection control is hard but familiar. On Mars, infection means medication use, sterile procedure burden, possible microbial uncertainty, crew exposure, and extra pressure on a medical system that was never meant to handle many serious cases at once. The condition itself is only part of the threat. The treatment burden is the rest of it. That is a key point. One sick person can consume far more than one person's share of colony resources. A medical crisis uses time, attention, oxygen, water, sterile materials, power, food, equipment, and expert labour. It may also use protected space that cannot be used for something else. So on Mars, one patient does not just create a medical problem. One patient can create a systems problem, and that is before you get to the microbes. A sealed habitat is not biologically simple. It is not clean in some permanent way just because it is controlled. NASA's work on host microorganism risk already points out that some microbes may behave differently, or appear more virulent in spaceflight conditions, while astronaut microbiomes and immune responses also shift. NASA is even testing better ways to detect antibiotic-resistant bacteria in orbit. That should tell you something very important. The biological environment inside a habitat is not static. People sometimes picture a Mars base as a sterile machine with humans living inside it. In reality, it would be a living microbial ecosystem wrapped around a stressed human population. Every person brings skin bacteria, gut bacteria, respiratory microbes, and a constantly changing biological profile. Every closed air system, water loop, surface, food area, and medical space becomes part of that environment. If immune function is altered and microbes are behaving differently, then infection control gets harder even before a clear outbreak begins. That creates a dangerous mix. The colony is closed, so microbes circulate through the same limited volume. The population is stressed, so immunity may not be normal. The medical inventory is limited, so treatment options are finite. The habitat is maintenance heavy, so a perfect sterility is unrealistic. And if resistant organisms start appearing or spreading, the colony may not have the diagnostic depth or pharmaceutical range needed to respond the way a hospital on Earth would. So the biological threat is not just Mars germs, and it is not mainly a science fiction infection from the planet outside. The more realistic danger may be the changing behaviour of Earth microbes living in an abnormal environment with abnormal selective pressures. That means the colony could be fighting illness inside a system where the microbes are adapting, the patients are stressed, and the medical staff are stretched thin. And all of this leads to the part people least want to say out loud. The first real Mars hospital may not be defined by its equipment. It may be defined by its triage rules. At some point, a colony may have to decide whose treatment justifies the oxygen, the surgical risk, the blood or fluid reserves if those even exist, the recovery bed, and the crew time. That is a brutal sentence, but it follows directly from the environment. If the settlement has only so much sterile space, only so many trained hands, and only so much life support margin, then medical decisions stop being purely medical. Who gets intensive treatment if 2 people are badly sick at once? Who gets pain control that uses scarce inventory? Who gets surgery if survival odds are uncertain, but the resource cost is huge? How much of the colony's capacity should be spent saving one person if doing so raises risk for everyone else? Those are not edge case questions on Mars. Those are questions the colony may need answered before it even launches. And that is where the entire mood of colonization changes. It stops sounding like exploration and starts sounding like lifeboat ethics. The colony may have to decide very early that some lives are less recoverable than others because the environment makes full rescue impossible. Once that logic becomes part of the system, it does not stay in the hospital. It spreads into governance, status, labour expectations, and social trust. People start asking who gets protected first, who gets treated first, and who is expected to accept greater risk for the group. That is why Mars medicine is not just about doctors and supplies. It is about what kind of society forms when rescue ends. A place with no evacuation, no external hospital, and limited biological margin does not simply practice healthcare. It starts building rules about which losses it can afford. And if that sounds extreme, the next problem makes it even more dangerous. Because on Mars, even small psychological strain and small communication delay can turn ordinary tension into a colony-wide governance problem. Mars is close enough to reach and too far away to help you. That is the real meaning of distance on Mars. People usually think distance is about kilometers. For a Mars colony, distance is really about time. Messages do not move instantly between Earth and Mars. One-way delays can reach about 20 minutes, and round-trip delays can reach about 44 minutes. There are also periods, like solar conjunction, when communication can be badly disrupted for extended stretches. That means there will be moments when the colony cannot ask Earth what to do and get an answer fast enough for that answer to matter. There will also be moments when it cannot ask at all. That changes the structure of the whole society. A Mars settlement cannot be run like a remote outpost waiting for instructions from home. It has to make decisions on its own because physics does not give it any other option. If a fire starts, if life support drifts, if a medical emergency happens, if a dust storm damages systems, if two departments both need the same power at the same time, the people on Mars have to decide with the information they already have. Earth can advise later. Earth can review later. Earth can criticize later. But Earth cannot step into the moment and take over. That sounds empowering when people talk about autonomy in a heroic way. In practice, it means permanent responsibility under pressure. The colony has to govern itself while knowing that some of its hardest decisions will be made without confirmation, without immediate backup, and sometimes without communication at all. That is not a side detail of deep space life. It is the core fact of Mars. And now add the human part, because autonomy under isolation does not leave people unchanged. Research from Antarctic winter-over missions has shown immune changes and psychosocial stress in isolated, confined, extreme environments. Analog programs like HISEAS exist for a reason. Delayed communication, monotony, shelf-stable food, confinement, and long mission timelines all affect behavior and performance. Sirius 21 and similar isolation studies show that human interaction patterns shift over long periods. People do not simply carry their normal social habits into these environments and keep functioning the same way. They change under the conditions. That matters because Mars crews will not just be co-workers. They will be each other's doctors, repair support, emergency backup, and only daily human world. The psychology of the crew is not a soft topic sitting next to the engineering. It is part of the engineering. If people become more irritable, less trusting, more withdrawn, more impulsive, or less cooperative over time, that is not just a morale problem. That affects maintenance, medical care, leadership, conflict resolution, and crisis response. On Earth, a bad social situation can often be escaped. You can leave the room, change jobs, go home, get help from other people, or simply create distance. Mars strips away almost all of those exits. The people around you are the people around you. The people you are tired of are also the people who may be needed to keep the settlement alive. So personal strain does not stay personal for long. And the evidence suggests isolation may reach even deeper than mood or stress. It may affect the brain more directly than people are comfortable admitting. Recent Antarctic winter-over research found temporary declines in grey matter volume in several brain regions, with some structural changes still present months after return. You have to be careful with analogies. Antarctica is not Mars, but the signal still matters. Extreme isolation is not just emotionally difficult, it may be biologically significant. Long periods of confinement and separation can affect the very systems a colony depends on for judgment, memory, social control, and resilience. That is a serious warning because a Mars settlement is built on decision quality. It needs stable judgment. It needs people who can manage frustration without blowing up team cohesion. It needs cognitive endurance. It needs people who can handle routine stress without becoming careless and emergency stress without becoming chaotic. If long-duration isolation chips away at those capacities, then confinement is not background discomfort. It is a direct operational hazard. And then Mars adds another layer on top of that. The colony is not asking people to make good decisions in a clean, calm environment. It is asking them to do it while other conditions are actively making good decisions harder. Elevated carbon dioxide is part of that picture. NASA and other research already link higher CO2 levels with symptoms and degraded decision-making. Add delayed communication, limited resources, sleep disruption, interpersonal tension, and an emergency, and now you have the real Mars decision environment. The colony has to keep solving difficult problems inside an atmosphere that may not always be ideal, under time delay, with no immediate outside rescue, while people are already carrying fatigue and stress. That means Mars does not just expose humans to danger, it can systematically weaken the conditions under which humans make sound decisions about danger. The crew may have to choose how to allocate power during a system fault while tired and breathing slightly elevated CO2. They may have to decide whether to risk an EVA during a worsening situation while communication with Earth is delayed. They may have to handle medical triage while already under social strain and limited sleep. Mars keeps creating moments where the people inside the system are asked to think clearly while the system itself is working against clarity. That is why small problems do not stay small on Mars. A misunderstanding can become a work slowdown. A work slowdown can delay a repair. A delayed repair can affect air, water, power, or heat. A technical disagreement can turn into a leadership crisis because there is no outside authority who can step in fast enough to settle it. A personal conflict can spill into scheduling, access to equipment, and willingness to cooperate under pressure. And that is where the danger becomes impossible to ignore. Conflict on Mars is not just bad team chemistry. It is a governance threat. If people on Mars disagree badly enough, the consequences are not limited to hurt feelings or a difficult workplace. Conflict can shape who gets EVA time, and therefore who takes the most physical risk. It can shape who gets scarce medicine. It can shape which department gets power during a shortage. It can shape whose repairs are prioritized and who is told to wait. It can shape who is ordered to take a dangerous outside job when something breaks. These are not ordinary management questions when failure means possible death. On Earth, dysfunctional institutions can limp along because the environment outside still supports life. On Mars, institutional failure immediately becomes more dangerous because the social order and the life support order are tied together so tightly. If trust breaks down, repair work breaks down. If repair work breaks down, survival margins shrink. If survival margins shrink, fear rises. And once fear rises inside a sealed habitat, every later conflict becomes harder to control. That is the deeper point. Mars governance would not be tested only by ideology or long-term planning. It would be tested by daily life under confinement, delay, and dependence. The people you cannot stand may also be the only people who know how to fix the recycler, calibrate the reactor interface, perform a medical procedure, or keep the oxygen loop stable. There is no real separation between social peace and technical survival. So when people talk about Mars autonomy, they often picture maturity and strength. But autonomy under these conditions can also mean being trapped inside your own mistakes, your own tensions, and your own bad decisions with no fast external correction. That is not just a psychological burden. That is a structural weakness built into the colony from the start. And once a society is forced to govern under those conditions, the next source of pressure becomes even more dangerous, because food is not just nutrition in a place like that. Food becomes leverage, legitimacy, and power, Food sounds like a supply problem. On Mars, it becomes a power structure. A lot of people talk about farming on Mars like it is the comforting part of the story. Greenhouses, fresh leaves, maybe tomatoes, maybe potatoes, maybe the first meal grown on another planet. That picture is emotionally powerful, but it hides the real issue. On Mars, food production is not a side project that makes the colony feel more human. It is one of the systems that decides whether the colony can be trusted at all. Plants matter for obvious reasons like calories and nutrition, but they matter for other reasons too. They can support oxygen production, help morale, support recycling loops, and strengthen the idea that the settlement is moving towards something more stable. NASA's crop research makes that clear, but the same research also makes something else clear. Growing food off Earth is not simple. You have to control light, water, nutrients, temperature, pressure, disease risk, contamination, radiation exposure, and crew time. You're not planting in a field. You're running a biological production system inside an engineered life support environment. That is why growing a few plants in orbit and feeding a city on Mars are completely different things. A small experiment can prove that life can grow. It does not prove that a colony can depend on it day after day, season after season, crisis after crisis. Dependable calorie base is not made of symbolic success, it is made of consistency. And consistency is exactly what Mars makes hard. We already have warnings about that from closed food systems on Earth. Biosphere 2 managed to produce most of its crew's nutrition, but it also experienced major atmospheric instability and difficult trade-offs. That happened on Earth, in a place with gravity, sunlight, intervention options, and much better access to tools and help. The lesson is not that growing food in a closed system is impossible. The lesson is that it's harder and more fragile than the optimistic version usually suggests. The same thing applies to orbital plant systems. NASA's veggie and plant habitat work is valuable, but those are tightly managed systems and relatively small-scale contributions. They are not proof that a Martian settlement can feed itself in a robust, routine, city-scale way. They show pieces of the path, not the end of it. And that distinction matters, because Mars colonization arguments often treat local food production as if it automatically reduces dependence on Earth. It can, but only after you pay for everything the food system consumes. That is the hard truth people skip over. Every kilogram of food grown locally only replaces imported mass after you have already spent water handling, lighting, nutrients, climate control, disease prevention, hardware maintenance, crew labour, and protected space to make that food exist. So farming is not free independence. It is an expensive conversion process. You're turning power, water, time, and reliability into calories. If any part of that chain weakens, the food system weakens with it. Who gets the freshest food if production falls short? Who gets the imported specialty items if resupply is delayed? Who gets the higher protein diet if a bioreactor underperforms? Who gets extra calories during heavy labour periods? Who gets nutritional priority if there are children in the colony later on? Those are not minor social questions. Those are the questions that tell people what the colony actually is. On Earth, food scarcity is almost never just about farming. It is about distribution, control, priority, legitimacy, and trust. Mars would make that even more direct, because the food system is artificial from the first day. Nothing about it is natural background abundance. Every tray, every crop cycle, every ration, every supplement, every reserve is visibly controlled by the settlement's technical and structure. That means rationing would not just appear during emergencies. Rationing logic could become part of normal social order. And once that happens, the food system becomes a system. People start measuring fairness through meals. They start measuring status through access. They start measuring leadership through whether they believe the distribution rules are honest. If one group gets fresh produce while another group gets shelf-stable rations, that is not just a dietary difference. It is a signal about hierarchy. If scientists, engineers, pilots, children, pregnant people, or outside workers all have competing claims on nutrition, then every food decision becomes an argument about what kind of society the colony thinks it is. And Mars makes that more dangerous because food can never be isolated from the rest of life support. Even success can create a new trap. Plants are attractive partly because they do so many things at once. They can support food, oxygen, fiber, waste processing, and psychological well-being. That sounds efficient, and it is. But it also means that crop failure is not just crop failure. If you lose a major plant system, you're not only losing fresh food, you may also be losing part of the air cycle, part of waste recycling, part of dietary diversity, part of morale, and part of the colony's own belief that it is becoming more self-sufficient. That is a dangerous kind of dependence because it ties symbolism to survival. A successful greenhouse is not only a food source, it is proof emotionally that Mars colonization is progressing. So if the greenhouse fails, the damage is larger than the calorie count. People see the failure and immediately understand what it means. It means the colony is less independent than it said. It means the settlement is still more dependent on imports than it hoped. It means one biological system took on multiple functions and has now opened multiple problems at once. And that can force very harsh choices, very quickly. Do you use limited water on crops or on reserve storage? Do you use power on lights for plants or on another critical industrial system? Do you preserve seed stock, feed the current population, or protect emergency reserves? Do you grow the highest calorie crops, the most nutritious crops, or the crops that best support morale? On Earth, those trade-offs are usually hidden by scale and abundance. On Mars, they are visible. That is why a hungry Mars colony would not just be stressed, it would be unstable by design. The moment the settlement has to choose between feeding expansion, feeding workers, feeding children, and preserving emergency reserves, it stops functioning like a neutral technical project. It becomes a place where survival priorities reveal social priorities. And once people stop agreeing with those priorities, food turns into a direct test of legitimacy. This is the part that makes Mars far more dangerous than the promotional version suggests. Food does not only sustain bodies, it helps sustain consent. People accept rules more easily when they believe the basics are secure and fairly distributed. The moment food becomes uncertain, every rule gets questioned harder. Why are we expanding if the current population is rationed? Why are some jobs rewarded with better diets? Why are some people protected while others carry the hardest labour? Why are emergency reserves being saved if current workers are breaking down now? And unlike on Earth, descent on Mars cannot spread out into a larger open society. It stays trapped inside the same sealed environment as the people making the decisions. The people angry about rationing still have to sleep near the people setting the ration policy. The people who think the system is unfair still depend on that system for the next meal. That does not make conflict disappear. It makes it more compressed, more dangerous, and harder to escape. So the food question is much bigger than whether plants can grow on another planet. The real question is whether a colony can build a food system stable enough, fair enough, and resilient enough that people still believe in the social order during shortages. And if the answer is no, then the colony does not just face hunger. It faces breakdown attached directly to the dinner table. And once you understand that, the next problem becomes even worse. Because even if food works and power works and habitats work, the colony is still tied to Earth by supply chains it may never fully escape. A Mars colony can look independent for years and still be completely dependent where it matters most. That is the next hard truth. People hear words like local industry, in situ resource use, self-sufficiency, and off-world civilization, and they picture a settlement slowly cutting the cord with Earth. But the timeline alone already damages that idea. Efficient launch windows between Earth and Mars open only about every 26 months, and the trip itself takes many months. That means every missing part, every damaged seal, every failed pump, every underpredicted medicine need, every broken suit component, every lost crop strain, and every electronics failure has to be thought about on a schedule that looks nothing like normal logistics. On Earth, modern civilization is used to fast replacement. If something breaks, a spare can often arrive in days or even hours. Mars does not work like that. Mars turns replacement into a long cycle problem. If the colony realizes it underestimated a supply, that is not a purchasing mistake. It can become a multi-season vulnerability. If a machine fails in a way engineers did not expect, the answer may not be order a new one. The answer may be live with the degraded system, improvise, cannibalize other equipment, or wait through a schedule that can feel almost geological compared with ordinary human planning. That is why Earth would not feel like a nearby partner. It would feel like a warehouse that is very far away and never available fast enough. And once you accept that, the real economy of Mars changes immediately. The real economy would not be mining first, or science first, or expansion first. It would be maintenance first. A Martian settlement would only survive by becoming extremely good at recycling, repair, substitution, and controlled degradation. It would have to become ruthless about keeping parts alive beyond their ideal service life, reclaiming useful material from damaged hardware, redesigning work around shortages, and turning every broken object into a possible spare parts inventory. That sounds efficient, but it also means the colony would be living in a constant state of industrial triage. And there is a limit to how far that can go. High recycling is not the same as full closure. High repairability is not the same as full industrial independence. Even on the ISS, where humans have huge operational experience and decades of accumulated learning, the logistics and life support chain is still deeply connected to Earth. Mars makes every one of those challenges worse. The distance is greater, the environment is harsher, dust contaminates everything, radiation stresses people and hardware, unknown failure modes are more likely. So the phrase "we'll fix it there" becomes a much harder promise when there is a place where tools wear down faster, spare parts are rarer, and consequences are much harsher if you fail. This is why maintenance stops being support work and becomes the core of the economy. The colony would not be asking, how do we grow fastest? It would be asking, how do we stop our systems from drifting into irreversible decay? That is a very different kind of civilization than the one often advertised. It is not a frontier of easy innovation. It is a place where survival depends on keeping complex systems alive far longer than they were originally meant to operate without a full industrial base behind them. And the dependence is not only physical, it is informational too. A Mars colony does not just need shipped mass, it also needs a functioning communications and navigation architecture, and a meaningful part of that architecture sits off the surface. Mars missions depend heavily on orbiters and relay assets to move data back and forth. Those assets do not last forever. They age, they degrade, they can fail. NASA has already had to manage relay capacity as Mars orbiters grow older. That is already a real operational issue, even for robotic missions. Now scale that up to a colony. A settlement would depend on communication not just for science data, but for operational coordination, software updates, planning, navigation support, telemetry, and probably a large share of its wider economic life. That means the colony is not only relying on what is inside its habitats, it is relying on a stack of infrastructure that partly exists above the planet, can age in place, and may be difficult to replace quickly. That is a dangerous form of dependence because it is easy to ignore until it starts weakening. If relay capacity drops, delays get worse, data bottlenecks get worse, coordination gets worse, mission planning gets harder, remote support gets weaker, navigation and situational awareness can degrade. And just like other Mars risks, this kind of infrastructure failure does not stay in its own category. It spills into everything else. Medical support becomes worse. Engineering support becomes worse. Supply planning becomes worse. Governance becomes worse because Earth and Mars understand each other more slowly and less clearly. So when people talk about independence, it is worth asking a direct question. Independent from what exactly? Not independent from Earth's factories, not independent from Earth's medicine pipeline, not independent from Earth's electronics base, not independent from Earth's communications stack, not independent from Earth's launch cadence. That means the story being sold to the public can get ahead of the industrial reality by a very large margin. And that creates a second danger. Mars may end up draining Earth more than protecting it. This matters because Mars is often framed as insurance for civilization. The pitch is that if Earth is vulnerable, building another branch elsewhere makes humanity safer overall. But if Earth is the one funding the launches, producing the spare parts, building the reactors, maintaining the relay network, developing the medical countermeasures, handling the planetary protection burden, and continuously sending advanced industrial support across interplanetary distance, then Mars is not acting like insurance in the short or medium term. It is acting like a long-term claim on Earth's most advanced capabilities. That becomes especially serious if Earth itself enters a period of strain. Climate disruption, economic instability, war, major supply chain shocks, or industrial decline would all change what Earth can keep sending outward. And the farther Mars remains from true autonomy, the more it starts looking less like a safeguard and more like a prestige project attached to a home world that may already be under pressure. That is the part many optimistic versions leave out. A dependent colony does not automatically reduce civilizational risk. It can increase pressure on the original civilization by demanding elite talent, high-end manufacturing, launch infrastructure, energy systems, medical research, and long-term focus all at once. If Earth is strong and stable, that burden may look manageable. If Earth weakens, that burden starts looking very different. And then the final point in this section becomes unavoidable. If Earth falters first, Mars probably does not become the survivor. Mars probably becomes the next casualty. A colony that can keep people alive for a while is not the same thing as a self-sustaining civilization. Those are very different thresholds. Real independence would mean being able to replace complex electronics, advanced materials, critical medicines, precision machine parts, power hardware, communications hardware, and high-performance industrial tools locally and reliably. That is an enormous standard. Until Mars can do that, its independence is mostly a story about perception. And if that independence is mostly theatrical, then Earth's crisis and Mars' crisis are tied together whether people admit it or not. If Earth's industrial system stumbles, Mars loses resupply. If Earth's research base weakens, Mars loses problem-solving support. If Earth's system fragments, Mars loses coordination and backing. If Earth's launch cadence collapses, Mars loses recovery options. In that situation, Mars is not a backup escaping Earth's vulnerabilities. Mars is another fragile system attached to them. That is the larger danger behind all of this. Coupled systems can fail together. And when people start calling one of those systems the backup, they can start making decisions that assume separation where separation does not really exist. That is how risk gets misread at the civilizational level. Not because the colony fails alone, but because both worlds were more connected than the story ever admitted. And once you see that, the next question becomes unavoidable. If Mars may never truly cut the cord, then maybe the biggest escape hatch people rely on is not self-sufficiency at all. It is terraforming, and that is where the story gets even harsher, because the planet itself may not have enough left to become what people want it to be. A lot of people treat terraforming like the future fix that makes every current problem less serious. That is one of the biggest mistakes in the whole Mars discussion. The logic sounds simple. Yes, the surface is bad right now. Yes, humans would need habitats, suits, shielding, pressure systems, and constant life support. But that is only the early phase. Later, once industry grows, once technology improves, once enough machines are working, people will change Mars itself. They will warm it, thicken the atmosphere, and slowly turn a hostile planet into something much easier to live on. That idea is powerful because it makes all the worst parts of Mars feel temporary. The problem is that the physics does not cooperate with that story. NASA's own summary of the Joukowsky-Edwards analysis makes the point very clearly. Present-day Mars does not appear to have enough accessible carbon dioxide to create the thick, warming atmosphere people usually imagine when they talk about terraforming. That matters because carbon dioxide is central to the popular version of the plan. The idea is usually that you release enough trapped carbon dioxide from the polar caps, the soil and other reservoirs, and that creates more pressure and more warming. But when researchers looked at the accessible reservoirs, the numbers did not add up to a transformed planet. The easy version of terraforming is not sitting there waiting for us. That changes the emotional meaning of the whole project. If Mars does not have the accessible ingredients needed for a major atmospheric upgrade, then terraforming is not a near-future engineering phase. It becomes a much more extreme and much more speculative dream. And once you accept that, you can no longer treat current survival systems as temporary scaffolding on the way to a normal planet. Then the next part gets even harder. The pressure gap is enormous. Mars has a surface atmospheric pressure around 0.6% of Earth's. That is not a small shortfall you make up with a few clever industrial steps. That is a planet-scale deficit. Even optimistic release of accessible carbon dioxide from known reservoirs falls far short of producing Earth-like conditions, or even conditions where humans could comfortably live without extreme pressure support. So when people talk about one day walking outside on Mars in light gear, or breathing something close to open air after a long engineering campaign, they are skipping over how huge the gap really is. This matters because it means the surface danger is not some temporary inconvenience waiting for enough investment. It is built into the planet at a very deep level. Mars does not just need improvement. It lacks the atmosphere and heat budget that make a surface broadly forgiving to human life. That is not the same thing as saying nothing can ever be changed. It is saying the easy mental picture is false. The planet does not seem to have the accessible material needed to become the kind of world the public usually imagines. And that has a direct effect on how people design the colony in the first place. If leaders, investors, or the public believe terraforming is a realistic phase change within some meaningful historical horizon, they may become more tolerant of fragile early designs. They may think of habitats as temporary. They may think of suits as a bridge technology. They may assume that the burden of shielding, pressure management, closed-loop life support, and protected indoor farming will slowly decline as the planet gets easier. But if the atmosphere is not realistically fixable with current or near-current means, then that assumption becomes dangerous. In that case, habitats are not temporary. They are permanent. Suits are not an early inconvenience. They are part of the long-term structure of life there. Shielded volume is not just something you need while the planet is young in human terms. It may be the defining limit forever. Airlocks, pressure integrity, life support loops, buried shelters, medical isolation rooms, and protected agriculture are not stepping stones to normal outdoor civilization. They are the actual form of civilization on Mars. That should change how every engineering choice is judged. If the artificial biosphere is permanent, then cutting corners becomes much more dangerous. Underbuilding is worse, temporary fixes are worse, delayed investment in redundancy is worse. You're not designing for an awkward first generation that will eventually hand over to a much easier world. You're designing for a civilization that may never graduate beyond controlled environments, and a world like that does not forgive mistakes. On Earth, if a city loses power, the crisis can still be terrible. But the atmosphere is still outside. Pressure is still outside. The open environment is still there, sustaining the body while people try to recover the system. On Mars, the planet gives you no such backup. If a city loses pressure integrity, there is no natural medium waiting outside to support life. If a habitat fails, Mars does not meet you halfway. It does not soften the error. It does not buy you time. It simply exposes the fact that the entire settlement was depending on artificial conditions every second. That difference is easy to blur when people talk about terraforming too casually. Terraforming language can make Mars feel like an underdeveloped Earth, like a place that is rough now but basically on the same path. It is not. It is a world where human life may remain dependent on sealed, engineered biospheres for the entire meaningful future of the project. That is a completely different civilizational model. And if that model stays hidden behind optimistic rhetoric, then the long game itself can become a trap. Think about what happens if humanity pours status, money, elite talent, industrial effort, and attention into Mars on the promise that one day the planet itself will become more accommodating. That promise can justify a lot. It can justify long-term subsidy. It can justify fragility in the early phase. It can justify risk because the hard years are framed as the price of eventual payoff. But if the physics never cashes that promise, then the whole structure changes meaning. Now, Mars is not a second cradle slowly becoming independent. It is a permanent high-maintenance project that keeps asking Earth for more support. More power systems, more spare parts, more medical innovation, more launch capacity, more protected habitats, more life support complexity, more patience. The colony may survive for long periods, but survival is not the same thing as becoming a self-sustaining world. An endless subsidy is not how a real second home for civilization should work. A true second cradle should reduce long-term dependence, not lock it in forever. If Mars remains a place where the environment never gets easier in the way people promised, then the project risks becoming a monument to technological persistence rather than a secure branch of civilization. It keeps demanding from Earth while never truly standing apart from Earth. That is why terraforming matters so much in this argument. Not because it is the only way Mars could ever host humans, but because the belief in it changes how people think about all the other risks. If the planet is not realistically going to become broadly forgiving, then every habitat stays critical, every suit stays critical, every air loop stays critical, every shielded tunnel stays critical. The colony does not outgrow dependence on artificial life support, it stays defined by it. And once you understand that, another question becomes unavoidable. If Mars may never become easy to live on, then what exactly are humans risking when they arrive in force? Because the next danger is that a human colony could damage the very science that makes Mars worth studying in the first place. There is another way Mars colonization could destroy something important, and it does not require the colony to fail at all. If Mars ever had life, then sending large numbers of humans there may be one of the worst ways to find it cleanly. That sounds backward at first, because the usual argument is that humans are better explorers. Humans can improvise, dig faster, make judgments in the field, and do more science per day than robots in many cases. But when the question is whether Mars hosts or once hosted life, human presence creates a contamination problem on a completely different scale. That is why planetary protection exists. NASA, ESA, and other agencies have spent decades building sterilization rules and special handling protocols because Mars is not just another destination. It is an astrobiological target. If there is any chance that Martian life exists now, or that evidence of past life still survives in protected environments, then contamination by Earth life is not a side issue. It goes straight to the core of the science. And the moment humans arrive in force, that contamination problem changes completely. A robotic mission is one thing, a human settlement is another. Humans bring trillions of microbes. They bring skin bacteria, gut bacteria, respiratory microbes, food systems, waste streams, water loops, crops, tools, clothing, vehicles, and constant interaction with the environment. Even with strong protocols, no living colony is sterile. Habitats leak at some level, dust gets moved, equipment gets reused, excavation spreads material around. Waste has to be managed somehow. At that point, the problem is no longer a few microbes surviving a launch and landing sequence. The problem becomes persistent biological traffic from Earth into the Martian environment. And once that starts, the scientific question gets much harder in a very specific way. If you find a biosignature later, what exactly did you find? Martian life? Earth life that escaped the colony? A mixed biological trace altered by human presence? A contaminated sample that can never be interpreted cleanly? That uncertainty can become permanent. You may never again be able to say with confidence whether a signal came from Mars itself or from us. That is why robots matter so much in this context. Robots can be sterilized much more aggressively than settlements can. For hardware going to especially sensitive environments, classic high-level sterilization approaches have included dry heat microbial reduction and other strict decontamination methods. That is hard enough with machines, but it is still a completely different category from trying to sterilize a living colony. You cannot dry heat sterilize people. You cannot sterilize food, crops, human skin, human lungs, human waste, and a full habitat the way you sterilize spacecraft components. A colony is biologically active by definition. So once people arrive at scale, the kind of scientific cleanliness that made Mars such a powerful target may be gone forever in the areas they touch. And because humans would want to go to exactly the kinds of places scientists care about most, places with water ice, interesting geology, subsurface access, and resource value, the overlap between settlement zones and high-value science zones could be especially destructive, and Mars is already hard enough to interpret even without us making it messier. Life detection on Mars is not simple. The chemistry is already tricky. Perchlorates and other oxidizing compounds complicate the preservation and interpretation of organics. Radiation chemistry changes things over time. Samples can be hard to contextualize. Surface conditions are harsh. That means even a clean search for life on Mars is subtle and difficult. Researchers already have to work carefully to avoid false positives and false negatives. Now add human contamination to that. Add Earth microbes, human organics, biological waste, industrial byproducts, excavation disturbance, and repeated local traffic. Suddenly the scientific problem does not just get a little harder, it becomes much more ambiguous. A positive result might be contamination. A negative result might mean the original context was destroyed. A weird signal might be Martian, human, or some interaction between the two. In other words, colonization could damage not just the environment itself, but the clarity needed to answer one of the biggest scientific questions humanity can ask. Did life emerge twice in one solar system? That is not a narrow academic loss. It is a civilizational loss. If humanity were to discover truly independent life on Mars, or even strong evidence that life once existed there, it would change biology, philosophy, planetary science, and our understanding of how common life might be in the universe. And if Mars turns out to have remained sterile despite once being more habitable, that would also be a profound result. Either answer matters enormously. Both answers help define humanity's understanding of life itself. That means Mars is not just another planet to occupy. It is one of the most important natural laboratories we have ever found. A rushed settlement could bury that laboratory under human biological noise before the core experiment is finished. That is the irony at the center of the issue. The same species that says it wants to go to Mars to answer whether life exists there could end up making that answer permanently harder to recover. And this is one of the few ways colonization can end something without a single dramatic disaster. It can end the pristine scientific Mars. It can end the ability to ask the question under clean conditions. Once human contamination reaches certain places, future generations may never get a second chance to study them as untouched environments. You cannot unmix a biosphere once enough contamination spreads. You cannot fully reset the experiment. You cannot go back to a pre-human Mars in the regions where settlement leakage, excavation and waste have already changed the environment. That is why the first humans on Mars would not just be inheriting a world. They would be choosing what kind of access the whole species retains to one of the most important scientific frontiers we know. If they move too fast or too carelessly, they may not only risk their own lives, they may erase the clean version of the question forever. And if that still sounds like a problem contained to Mars, the next section gets worse, because the biological traffic does not only threaten the red planet, it can also threaten Earth. Mars does not only raise the risk of contaminating another world, it also raises the risk of bringing new biological problems back to Earth. That point can sound exaggerated at first, because people hear planetary protection and think of science fiction. But backward planetary protection is not some paranoid movie idea. Serious scientific and policy work already treats protection of Earth's biosphere as a real design problem. That is why sample return from potentially life-bearing environments can fall under restricted Earth return logic. The point is not that scientists know Martian life is dangerous. They do not. The point is that when the uncertainty is high and the stakes are global, the correct default is containment first. That is a very important distinction. You do not wait until the danger is proven when the consequence could involve an entire biosphere. You design as if you might be wrong, because if you are wrong in the wrong direction, the cost is too high. That logic already exists for carefully controlled sample return, and if that level of caution is justified for a limited set of sealed samples, then a human Mars program raises a much bigger issue. A sample return mission is one thing, a settlement is something else entirely. With a sample return campaign, you can build multiple containment layers. You can use restricted facilities. You can carefully manage every handoff. You can heavily constrain what touches what, who touches what, and where material moves. The whole point is to keep the chain controlled from beginning to end. A colony breaks that model open. Now, you are no longer talking about one sealed sample container moving through a narrow path. You're talking about continuous traffic, hardware going out, people coming back, suits being reused, regolith being handled, ice being processed, waste being managed, manufactured products being shipped. Maybe one day biological systems engineered for Mars use being moved between worlds. The scale difference is enormous, and the scale difference changes the nature of the risk. The more material and biology move between Earth and Mars, the more chances you create for something to go wrong. Not always because of one dramatic mistake, sometimes because of slow drift, sometimes because a process that looks strict at first becomes routine, sometimes because people get used to success and stop treating the system like it can fail, sometimes because schedules get tighter, money gets tighter, and exceptions start getting normalized. In a long-running Mars program, the danger is not just one breach. The danger is a gradual culture shift where the system becomes less careful than the stakes require, and there's another point people often miss. The uncertainty is not limited to hypothetical native Martian life. Even if Mars turns out to have no indigenous life at all, a colony can still create biological novelty. NASA's work on host microorganism risks already shows that microbes and human microbiomes can shift under spaceflight conditions, and human immune systems can shift too. Space habitats are strange biological environments. They combine radiation, confinement, stress, altered gravity, recycled air, controlled water systems, limited microbial diversity in some ways and concentrated diversity in others, and constant engineering control over the environment. That means a mature Mars settlement would not just contain humans. It would contain an evolving microbial ecosystem under unusual selective pressure. Earth microbes inside that environment would not necessarily behave exactly the way they behave on Earth. That does not mean some dramatic movie scenario where a Mars plague suddenly appears. That kind of framing is too simplistic. The real concern is more sober, and in some ways more realistic. The concern is that a long-duration off-world habitat could become a place where familiar microbes change in unfamiliar ways. That possibility should be treated seriously, not because panic is useful, but because biology under extreme conditions can produce surprises. If you have altered immunity in the human population, radiation in the environment, chronic confinement, unusual cleaning regimes, tight recycling loops, heavy antibiotic use or limited antibiotic inventories, and a closed population, you are creating conditions that deserve careful biosecurity thinking. A Mars colony could become a biological environment that is different enough from Earth to matter, even if Mars itself is sterile. And now the problem stops being only technical. Civilization is not very good at handling low probability, high-stakes warnings once major money and prestige are attached to the system. That pattern shows up again and again. At the beginning, everyone agrees that strict rules matter. Then the project grows. More actors get involved, more deadlines appear, more public symbolism gets attached, more funding depends on momentum, more careers depend on keeping the machine moving, and slowly exceptions start becoming easier to justify. That is exactly the kind of pressure planetary protection rules would face if Mars became economically valuable or culturally sacred. Once settlement becomes a symbol of national greatness, human destiny, economic expansion, or civilizational survival, containment rules no longer operate in a calm scientific vacuum. They operate inside systems that reward speed, optimism, and public success, that is when discipline starts eroding. And containment culture usually does not collapse in one obvious moment. It erodes through repeated small decisions. One process gets simplified because it is slowing things down. One shipment is treated as low risk because previous shipments were fine. One quarantine step is shortened because the pressure to move faster is intense. One inspection becomes more relaxed because everyone involved thinks the danger is mostly theoretical. One company argues that stricter controls are blocking progress. That is how a risk culture weakens. Not because people stop understanding the principles, but because the incentives start rewarding exceptions more than caution. So yes, a Mars project could absolutely boomerang back onto Earth. But the most realistic version is probably not some giant science fiction outbreak. The more plausible danger is a governance failure. It could be a contamination failure. It could be a biosecurity failure. It could be a failure of scientific integrity where materials are moved, interpreted, or released under pressure that the system was never honest enough to resist. It could be a failure caused by overconfidence in containment procedures that looked solid on paper, but were too complex to remain perfect over years of repeated human use. And that kind of failure matters because once you are running a civilization that bridges biospheres, a breach is no longer local by definition. That is the deeper problem. Earth and Mars would not just be exchanging cargo, they would be exchanging biological risk, uncertainty, and responsibility. And the more normal that exchange becomes, the easier it is for people to forget what kind of system they are actually operating. They start thinking in terms of routine transport, routine personnel movement, routine materials handling. But biology does not care whether the system feels routine. If the process is flawed, it only takes one meaningful breach to prove that routine was the wrong word all along. That is why the Mars debate cannot honestly stay inside the frame of engineering optimism. The moment you create regular traffic between worlds, you are no longer just building habitats and vehicles. You are building a long-term interface between biospheres, between microbial ecosystems, and between governance systems that may not deserve the level of trust they are being asked to carry. And that leads to the final step in the argument, because the real extinction path is not one dramatic disaster. It is something worse. It is many risks coupling together until the whole project stops being a backup for civilization and starts becoming a way of weakening it. The biggest danger in a Mars colony is not one dramatic accident. It is a chain of problems that start reinforcing each other. That is the part most Mars debates get wrong. People often argue in a very narrow way. They ask whether humans can survive radiation, or whether dust can be managed, or whether food can be grown, or whether reactors can work, or whether medicine can be done remotely. But that is not how failure usually works in a place like Mars. The real danger is not that one problem is instantly unsurvivable on its own. The real danger is coupling. Radiation weakens people over time. Low gravity deconditions the body over time. Dust damages hardware over time. Carbon dioxide drift can reduce judgment. Isolation strains teams. Sleep gets worse. Medical capacity stays thin. Power holds every critical system together. Logistics are slow. Spare parts are limited. On their own, each of those may sound like something a determined colony could handle. But Mars does not present them one at a time in a neat order. Mars lets them overlap. That is where the risk becomes much more serious. A tired crew deals with a maintenance delay. The maintenance delay affects air handling. Slightly worse, air makes the crew slower and less sharp. Slower work delays another repair. A dust issue reduces power margin. Lower power margin forces trade-offs. Trade-offs increase stress. Stress increases conflict. Conflict weakens coordination. Weak coordination makes emergency response worse. None of that has to be a single spectacular disaster. It just has to synchronize badly enough. And that means Mars colonization is not mainly a bravery test. It is a complexity gamble. Every time the colony grows, it becomes more capable, but it also becomes more complicated. Add another habitat and you add more protected volume, but also more seals, more valves, more sensors, more piping, more heating load, more maintenance. Add a crop chamber and you add food production, but also disease risk, water demand, lighting demand, contamination risk, and another system that can fail. Add a reactor and you add stable power, but also another layer of maintenance, spare parts, safety procedures, and technical dependency. Add a mining rig, an airlock, a transport route, a medical bay, a child, a school space, a manufacturing shop, and the same pattern keeps repeating. Capability goes up, but the number of interacting failure states goes up too. On Earth, complexity is buffered by a planet that is already alive. If one building fails, the atmosphere is still there. If one region has a bad harvest, food can move from elsewhere. If one hospital is overloaded, others exist. If one machine part breaks, an industrial base of enormous scale can often replace it. Earth gives human systems a huge amount of hidden forgiveness. Mars gives almost none. That difference matters more than people admit. Complexity without forgiveness is where civilization becomes brittle. The more advanced the colony gets, the more it may depend on everything working within narrow limits all at once. It can start to look stronger because it has more systems, more volume, and more people. But underneath that, it may actually be developing more ways to fail in combinations no one fully predicted. And the most dangerous version of this is the version sold as salvation. If Mars is marketed as species backup, as the place that protects humanity if Earth becomes unstable, then that story can start changing decisions here on Earth. It can justify shifting money, urgency, elite talent, and public imagination away from protecting the biosphere we already have. It can make people more tolerant of risk because they think a second branch of civilization is being built somewhere else. It can even make Earth's own fragility feel less final because the story says there is now a plan B. But current science does not support that level of confidence. For the foreseeable future, Mars remains deeply dependent on artificial life support, heavy shielding, robust power, intensive maintenance, and long supply chains from Earth. That means you are not building a true second cradle in the near term. You're building another fragile system, and it is tied directly to the first one. That is the part that turns the backup story upside down. If Earth weakens, Mars does not automatically become safer. It may become weaker too. If Earth's economy is under stress, Mars' resupply gets harder. If Earth's industrial base stumbles, Mars loses replacement parts and technical support. If a Mars crisis demands more resources, Earth may have to divert even more to keep the colony alive. So instead of one resilient world plus one backup, you may end up with two fragile systems linked tightly enough that failure in one intensifies failure in the other. And that brings the argument to the main question. How could Mars colonization actually end humanity? Not necessarily by killing every human being. That is not the most realistic path. The more realistic path is something almost as serious in historical terms. Humanity could lock itself into a prestige megaproject that weakens resilience on Earth, creates a dependent off-world population, normalizes extreme risk as destiny, adds new contamination and biosecurity burdens, and then runs into a synchronized systems crisis that damages both worlds at once. Picture the shape of that crisis. Earth is already under strain from climate stress, economic strain, conflict, or resource pressure. Mars still depends on Earth for critical support. A major Mars failure then happens during a bad time. Maybe power degrades during a dust event. Maybe medical and life support issues overlap. Maybe communications are degraded. Maybe a contamination controversy or governance failure explodes at the same time. Suddenly the colony needs emergency support, but Earth is less able to provide it. Public trust breaks, huge amounts of capital are burned. Vital technical talent is tied up in rescue, blame, and emergency redesign instead of strengthening Earth systems. The colony suffers, Earth suffers, and the original promise of resilience starts producing the opposite. That is what civilizational self-maiming can look like. Not one explosion, not one heroic tragedy. A deep, expensive, demoralizing systems failure that damages confidence, institutions, and long-term capacity all at once. Recovery from that kind of event is not guaranteed, especially if it happens during a period when Earth is already unstable. And there is another reason this matters. Civilizations do not only depend on hardware, they depend on judgment. If enough people commit to a project for the wrong reasons, the project can keep absorbing more resources long after the evidence has turned against the story used to justify it. That is one of the darkest possibilities in the Mars debate. Not simply that Mars is hard, but that humanity may keep escalating commitment to Mars because admitting the limits would be emotionally and culturally painful. That is why the final twist is so uncomfortable. Mars is often framed as the place where humanity proves it can survive anything. But the darker possibility is the opposite. Mars could become the place where humanity proves that intelligence alone is not enough, courage alone is not enough, and technology alone is not enough. If you misread a tightly coupled system as a frontier, you can simply push through. A brutally coupled system does not care how inspiring the mission sounds. It does not care how brave the crew is. It does not care how badly a civilization wants the story to be true. If the system requires near-perfect performance from weakened people inside fragile machines on a world with almost no natural forgiveness, then belief does not make it robust. Ambition does not make it stable. Repetition does not make it safe. That is the real warning inside the idea of Mars colonization. The Red Planet does not need to defeat humanity in some dramatic final battle. It only needs humanity to overestimate itself. It only needs us to mistake partial capability for true security, technical survival for civilizational viability, and a dependent outpost for a genuine second home. And if that mistake is big enough, Mars would not save humanity from collapse. It could become one of the ways humanity helps bring collapse closer. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.